Recorded is rolling. Welcome to Friday. Getting near the uh, end of the week here. Yeah, so a couple periods left. Of course, Friday we got short days, and we won't even have a seventh period, so not super whole lot I can do today. But I do want to fit in a couple of things. So got to try this school, so there you got some tidbits that hopefully you can get something out of this class. Okay, so one thing is I do have a fun activity lined up for you guys, but before we get to that, we talked a little bit about uh, variables and units. But you know what you might see on your desk are some pages that look like this. Oh.
Good afternoon, dear. At this time, teachers will ask you to take a seat and for your seniors to the gym. At this time, we're asking for teachers to take a minute and for your seniors to the gym. Thank you.
All right, and so double check. We have no seniors in here. I think it's right. Okay, so we'll hang out here and have a good time with the nap on the moon activity. We'll get to it. First, variables. Right, so these are ready-made flashcards, variables, and units. I want to show you guys some examples. How about yesterday you guys were measuring radius of a circle, right? That could be like R, could be radius, but you might see capital or lowercase. Okay. Now, what's on the direct backside of that section of the paper? Says radius is measured in meters. Right? I mean, you could do feet or inches, but we're going to tend to use metric system. Yesterday, you guys did centimeters. That worked. Okay. So, for example, radius equals 3.0 meters could be a radius, right? For example. Okay. There's a bunch of other ones on here too. You know what? If you guys want to steal this page and cut it up and use them for flashcard yourself, then go ahead. If you want this file and you don't have access to it, then it is on Google Classroom. I got it on Google Classroom this morning. And I want to do some more examples with you guys. Because this is just one of those little things that you get down earlier in the year. It's going to help you down the line. Okay. Suppose you measured a different circle. And let's say it had a radius of 11 centimeters. Because do you want to do this in physics? Do you want to say, oh, the number of centimeters equals 11? Is that what you want to write in this class? No. How about this? Would you want to write radius? Not with that pen now. Got out of ink. Do you want to write radius is equal to 11 centimeters? Is that the way you would write that? Yeah. Because look what you have here. You have a variable and a unit. And then the 11 represents magnitude, right? So I guess three things we're looking at, right? Variable, magnitude, and a unit. Right now, you guys know numbers, say from a math class, you can spot those. But whenever you see letters in this class, it could refer to one or the other of these. It could be a variable or as a unit. Let's do some more examples. I think you guys will see. Where's some other things to measure? Oh, how about this? I got a whole box of lab masses here. You guys get your hands on these for plenty of labs. The biggest one here is 1 kilogram. For context, that's approximately 2.2 pounds, but 1 kilogram in that metric system. Suppose you had three of these guys. Would you want to say the number of kilograms is equal to 3? Is that what you want to say? How about this? What do you guys think the variable is for mass? Mass. What do you guys think? M? Good call. Yeah, you guys are on. Mass is equal to 3 kilograms. Oh, look what we got, just like before. You got the variable, M, you got the unit, kilogram, right? You guys got? Okay. How about let's see, where's this line up on this page? Where's my, here it is. So M is a variable. If I flip it over, it's on the exact opposite side. Mass, measuring kilograms, for example. Oh, that's exactly what I gave you. Look at that, 3.0 kilograms. Gets it? Okay. Now, the letter M you have to be careful with because as a unit, it stands for mass. But as a I got that wrong. Okay. As a variable, it stands for mass. Okay. As a unit, it could stand for meters. Okay. You might also see it as a prefix milli, like 1/1000th, like millimeter or milligram. And also, you guys have seen another context for it too, which is the algebra form stands for slope, like y equals mx. So m gets used a lot of different contexts. In the context you see it right here, this is as a variable. Okay. And up here, this one is like a unit, like centimeter. How about Oh, you know what else I want to mention? Just since I read it here, next week we're going to talk a lot about basic stuff too, including precision and accuracy. Guys, is there a difference between 3 and 3.0? Not in a math class, but in a physics class, does that 0.0 mean something? Yes, right. It tells you have more precision. See, if I just wrote 3 and just something said just plain 3 kilograms, well, that might be 3.1 kilograms, or might be 2.8 kilograms. Like this would all round to 3. So that'd be fine in terms of like one significant figure. But if I say 3.0, that means I have that level of precision, right? I know it's not 3.1, it's not 2.8, it is like different. Now it might be 3.04, might be 3.03, might be even 2.99, but it's yeah, I do know like 2 digits. How about this? Let's say you're watching the time go by, tick, 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 and you count off 7 seconds. Do you want to say the number of seconds is equal to 7? You want to do that? How about this? What do you guys think the variable is for time? Time. What do you think? T. Good call. You guys are on. Time is equal to 7 seconds. How about that? Does that work? Bing. That work. Look, variable unit. Variables T time. Unit is S seconds. Let's do one more. Let's say you're pushing something around. Right? So let's say put a force on this. That's all a force is, just a push or a pull. So force is a push or a pull. Right, so go ahead, a few weeks in this class, but pushing on this thing, it's causing it to move, right? Or you know what? This thing also has a weight that's pulling it straight down. It's like a gravitational force pulling it straight down. Right? What do you think the variable is for force? Force. What do you think? Good call. Oh, you guys are on. Okay. Does anybody know a unit to measure force, like a push or pull? What's one unit you can use to measure force? I bet you guys know something. Tell you what, Newtons. Yeah, actually, that's the best answer. Newtons. Let's say you push with like 10 newtons of force. You might say 10 newtons. Yeah, but force could be 10 newtons. You push with so many newtons. Okay. If you were thinking pounds, that could also measure force. Although pounds is tricky, that's a different system. I'm almost never going to use pounds in this class because that's not metric system. That's like from the English system. But pounds is ambiguous because it's used for both mass and weight, which is like super icky. But the metric system keeps mass and weight distinct. You know, I was going to tell you guys this stuff next week, but you know what? Why not? Maybe you guys hear this twice. Weight is like a force, and mass is like the amount of matter and also an amount of inertia. So like this 1 kilogram right here, that's 1 kilogram of mass. Okay, guys, if you were floating around an International Space Station and like pass this back and forth, like throwing it back and forth like a tennis ball, you think it would take some force to throw it and some force to catch it, even though it has no weight, it's just floating around, right? Hey, what would you rather catch if somebody throws something straight at your face in the International Space Station? Do you want to catch this, or do you want to catch this little guy? What do you guys think easier to catch? Probably easier to catch the little guy, easier to stop them, right? Even though neither of them has any weight, just floating around in space, but this one has a lot less mass, a lot less inertia, right? Now, weight is a type of force. It's like a gravitational force. A force is actually a push or pull. So both these objects, even they have different amounts of mass, but then there's gravity force each pulling them straight down. Right? That's a weight. Okay? So different amounts of weight. Right? All right. All right. That's enough on variables and units. All right, you guys ready for fun team activity today? Okay, so you might see a grid on your desk. Looks like this. Yeah, it should have some more printed, but there might be a few short, but we got what we got. Okay. So there's a list of items, and I've got a story to tell you guys. A story that goes with this list of items. And all right, so it goes like this. NASA exercise, survival on the moon. All right, now this story has some details in it. Pay real close attention to details. You know some stuff about science. Gonna have you guys help each other out with the task that you guys about to get. So here's the story. You are a member of a space crew originally scheduled to rendezvous with a mothership on the lighted surface of the moon. Pause right here for a moment, because if you're in the daytime of the moon, it's light outside. Does that feel like a nice warm sunny day, or is it like, oh, I'm in an oven and I'm being baked? What do you guys think it feels like? Yeah, it's like in an oven. What if you step in a shadow on the moon? It's like, oh, nice little shade. Or it's like, oh, I just stepped into a freezer. What is that? Like step into a freezer? Okay. Why is that? Why is that on the moon? In the sunlight, you're like in an oven, and in the shade, you're like in a freezer. Why is that? Because the moon has exactly the moon has no atmosphere, right? No atmosphere. Right? That might help you out. Maybe I'm giving you guys too many hints here, but you guys know. However, due to mechanical difficulties, your ship was forced to land at a spot some 200 miles from the rendezvous point. For context, that's like almost exactly from here to the border with Georgia. So if you walk from here to Georgia up I-95. During re-entry and landing, much of the equipment aboard was damaged, and since survival depends on reaching the mother ship, the most critical items available must be chosen for this 200-mile trip. Below are listed the 15 items left intact and undamaged after landing. Your task is to rank order them in terms of their importance for your crew and allowing your crew to reach the rendezvous point. Place the number 1 by the most important item, number 2 by the second most important, and so on. 15 would be the least important. Okay, so let me throw some tidbits and hints that you get for you guys. The way we're going with this is here. There's different columns on this paper. I know I'm a few papers short, but see you this. There's one for your own personal ranking. There's one for your team ranking, and then closer to in the class today, I'm going to give you guys the official NASA ranking, right? What they came up with. We'll treat that as like the answer key, right? Then I'm going to have you guys take a difference, right? Now take the positive difference. We're just looking at absolute values. Then I'm going to have you guys total it at the end. Have you guys do it for yourselves individually and also for your team. And almost always what happens is that if you work as a team, your score improves. Guys, what would be a perfect score? See if you guys are following.
A 100. Oh, is 0 as in 0 things incorrect?
0. Yeah, exactly. You got it. Right, because let's say I'm just gonna make up some numbers. Let's say the box matches was ranked 5 and you also ranked it 5. So the answer is 5 and you said 5. The difference would be 0, which means that you got it exactly what they said. And if you did that for all the way down the list, then your final score would be 0, and that would be perfect, right? Now it's hard to get perfect. This is actually a pretty tough puzzle. But yeah, I will give you guys some time. I'm going to pause this recording and come back in a few minutes and see how you guys did. Right, and pause. Right, recording is resumed. Just give you guys a couple hints I meant to give you. Right, so one thing is don't worry about think about like the size of these objects or like how bulky they would be to carry around. Just rate them strictly on utility. And kind of going hand in hand with that, they do mention the weight of the tanks of oxygen. Again, see that unit right there, pounds. Right? You'll almost never see that in this class because that's not part of the metric system. And pounds is ambiguous because it could refer to like mass or weight. It's like, well, what do they even talk about there? Versus metric system, it's either kilograms or newtons, so it's very distinct. But I'll tell you just because I know the answer key, they are referring to weight. Now, because they're referring to weight, is the weight different on the moon? Yeah. Does anybody know what fraction of weight you are on the moon compared to Earth?
About an 8.
Yeah, about 6. Yeah. So take this divided by 6, and then that's the equivalent weight on the moon. Okay. Does your mass change on the moon? The amount of matter, the amount of inertia? No, your mass is the same, but your weight is 1/6. All right. So there's a couple of hints. All right, and let me pause this recording again and keep on going. Resume recording. So, you guys ready to check yourselves? See how you did. All right. So. Okay, answers. Oh, refocus this thing. Okay, box of matches. You guys rank that high or low?
Low.
They put it dead last, so good call on low. It says virtually worthless because there's no oxygen on the moon to sustain combustion, right? Yeah, and you guys said that too. Hey, side note about that. So we're in Earth's atmosphere, so we're in air. Air is a mix of different gases. What's the predominant gas in the mixture of air in this room? It's mostly what?
Nitrogen, right?
Nitrogen. Yeah. It's, I think it's what almost 80% nitrogen. It's like 78%.
73.
So something like that.
76.
In the 70s. Yeah. And it's about 20% oxygen, and then little amounts of yeah. But yeah, on the moon, yeah, no atmosphere, no oxygen. Yeah, you can't light a match. Right? Food concentrate. 4. Efficient means of supplying energy requirements. As an engineer way to say people get hungry. 50 feet of nylon rope. ranked number 6. Useful when scaling cliffs and tying injured together. Parachute silk. They ranked 8. It says protection from sun's rays. Now, think about that a little bit, because in the premise, they did say you were on the lighted side of the moon, right? And you guys know that would be like being in an oven. You probably have an astronaut spacesuit that's going to help you out quite a bit on that front. But how long is a lunar day? Like, how long does it take to go from day to night, like one full cycle? What do you guys think?
And I believe it's totally locked, isn't it?
Right. Yeah, that's an important part of this. Yeah, the moon is tidally locked to Earth, right? You guys do know that only one side of the moon ever faces Earth. Like, we never even knew what the other half of the moon looked like until we just set rockets up, like it started a few decades ago, right? I had no idea. Yeah. Okay, so that can help you figure this out, right? So how long does it take the moon to rotate once?
It doesn't rotate.
Right. Yeah. Okay. So relative to Earth, right? So its rotation would be aligned exactly with one revolution, which would be 1 year. Mm-hmm. 1 month, right? Right. And how about the root word of month? It starts with the letters what? MO? Just like moon. Right. So where that comes from. Yeah. So to go from to go from, let's say, dawn to dawn would be like 1 full month. So probably at least a couple of weeks. I'm thinking until we get to nighttime. So like walk from here to the Georgia border, because this is probably about 200 miles. Yeah, if you could get there within a week or two, you're probably going to be in daylight the whole time. Right? Okay, yeah. So portable heating unit 13, not needed unless on the dark side. Okay, actually, these two kind of go together, right? Because now, if you thought you were going to land in nighttime before you reached the mothership, well, I bet this is going to go way up on the list, right? But if you think it's going to be daytime the whole time, then yeah, probably chuck it. 2 45 caliber pistols is listed as 11. And the explanation I have here is possible means of self-propulsion. I guess that's American transportation. Pew, pew. Earlier today, some other students brought up a good point. That's probably not the real reason for that. I don't know. If you're like a spy in the old Soviet Union or something, they might give you some like suicide tablets. I think I have a suspicion that's what that's actually about, but I guess we're in school, so we're gonna do self-propulsion. Pew! 1 case of dehydrated milk. All right, pause right here. Let me grab this phone call. Recording is resumed. All right, dehydrated milk. What's number 12? Bulky or duplication of food concentrate. 200-pound tanks of oxygen. Listed number 1. The most pressing survival need. And of course, the translated weight would only be 17 pounds on the moon. Yeah, gotta breathe. Stellar map. What'd you guys rate the stellar map? High or low? Hey, how are you going to navigate on the moon?
Compass.
I'm gonna use the stellar map. Primary means of navigation. Star patterns are. It says essentially identical. It really just say identical. The star patterns would be identical on the moon as on Earth. So,
Lunar. That be moon.
Okay. So stellar map is just like a map of the stars, like where all the stars are. Yeah. So you're trying to like figure out like which way is like north. The North Star would still be like in that direction, right? Orion's still where Orion is, right? Yeah. In fact, yeah, if you go back like a couple thousand years ago, people could read the night sky the way we could just read a book. You pick it up and just take it for granted. Oh, words. Oh, okay, I know what that means. Right, read that sentence.
Yeah, it was a big part of navigation. Like, you didn't have GPSs, so they literally just looked at the stars and was like, oh, I will by degrees.
Right. Yeah. Exactly. You could pretty well know exactly what latitude you're at. Just they could glance at the sky way back in the day. He's like, oh yeah, I know exactly what latitude. Right. Yeah. Okay. Self-inflating life raft. They listed number 9, carbon dioxide bottle, and the military raft. Okay, I guess it's military now. May be used for propulsion. Oh yeah, more American transportation. Pew pew. Magnetic compass. What do you guys say? High or low? Let's place it, yeah, near the bottom, 14. Now why would that be? How does the compass work? Well, they've got the magnetic field on the moon. There's no magnetic field on the moon, right? So magnets align to Earth's magnetic field, right? Here, let me show you guys got a bar magnet, got a field indicator. You guys see like this would be like a cross section of the magnetic field. You guys can kind of see these field lines, right? And Earth is basically like a giant magnet. So if you have one of these, if I hung this from a string, we'll do this probably next semester in Newman, right? If you hang this from a string or put this in like a bucket of water, its poles will actually align north and south. And you can just make a rudimentary compass real easy. But on the moon, it doesn't work because there's no magnetic field on the moon. So the compass, worthless. Let's 20 liters of water. So number 2, needed for a replacement of tremendous liquid loss on the light side. That is the engineering way to say people get thirsty. Signal flares. This one you guys brought up a good point that those matches are worthless. What about the flares? I did look this up, and at least according to a guy named Tom on the internet, he says, sure, a signal flare will work on the moon, but you have to make a special one. The flare has to have both the material that burns, usually magnesium, which burns brightly, and oxygen. You can create it, just package it all in one, and you can even burn them underwater, blah, blah. It talks about some examples. So yeah, that's straight from Tom off the internet, so must be true. We're going to go with, they listed it number 10. They said use as distress signal when the mothership is sighted. So see a mothership, shoot off some flares, pew, pew, and they might see you. First aid kit, including injection needle, listed number 7. Needles connected to vials of vitamins and medicines that will fit a special aperture in the NASA spacesuit. And solar-powered FM receiver transmitter listed 5 for communication with the mothership, but it'll only work when you have a line of sight with the mothership. So the transmitter, you can send out a signal, receiver is just like, turn on a radio, you can tune in, receive communication. I'm so sorry, guys. We only got 30 seconds of class, but at least I'll show you here. So find all the differences between yours and the key, add up the differences, and here's the scoring key. So I've got 0-25, which is really hard to do. That's excellent. 32 is good. 33 to 45 is average, and so on. So there you go. You can find your score. Hope you guys enjoyed that. All right, you guys have a great weekend.